The K-series engine from Rover. The engine that sets new standards in performance and reliability. This program reveals some of the design concepts of the K-series, and during an engine rebuild sequence we'll examine its new features. The A-series engine had been continuously updated since its introduction in 1952. As a result, it remained highly competitive both in terms of performance and economy. However, engineers realized that it wouldn't remain so for much longer unless significant design changes were made. In 1984, the decision was made to start from scratch and design a completely new range of engines. This project was to become known as K-series. But what was the design team's initial concept for K-series?
The design concept started as a complete replacement for the A-series engine in our small and medium range cars. A-series had really been taken about as far as it could go, so we were after a modern, up-to-date engine which could suit the new generation of cars, meet the new legal requirements in terms of emissions, provide good fuel consumption, and generally take us into the next century for our powertrains.
High performance, good fuel economy, and good emissions. All three of those together. It's always been possible to do one and perhaps two, and the challenge was to do three, and this is where we had to have real proper control of the combustion process, and we were going to get all three of those.
Since the late 70s, engineers at Gaydon had been involved in a project to design and build an energy conservation vehicle to test and validate new ideas. The prototype was capable of speeds in excess of 115 miles per hour and 63 miles per gallon, all from a three-cylinder 1100cc engine. A single-cylinder research engine was used to evaluate combustion chamber design. Computer wireframe models were used to calculate combustion chamber and inlet port profile. Plastic combustion chambers were machined directly from these computer models and flow tested to ensure they gave the correct swirl of inlet gases. The best of these designs were manufactured in alloy and fired up on the research engine. A A fundamental design requirement of the new small engine range was lightness. Aluminium alloy castings are lighter than cast iron, but in most engine design this advantage is lost because larger castings were needed to compensate for aluminium's lack of tensile strength. Rover engineers tackled this problem in an ingenious but simple way. In essence, they removed the tensile loads from the castings. In the new engine design, the main components, cylinder block, cylinder head and bearing ladder, are held together in compression by long through bolts, which carry all tensile loads produced by the engine. Advanced LPS casting techniques previously pioneered on the M16 engine reduce weight even further. Low pressure is applied at the base of the mould to assist the flow of molten alloy. This allows the use of more intricate designs with thinner, lighter wall sections. All this design innovation, development and extensive testing produced the K-Series family of engines. The K-Series lineup consists of 3 engines identified by their capacity and valve count. There are 2 8-valve or K8 engines, one of 1120 cc's and the other of 1397 cc's. The K8 engine has a belt-driven single overhead camshaft which operates the valves through hydraulic tappets. Fueling for the K8 engines is provided by a new constant depression KIF carburetor. A high-performance K16 engine tops the range with belt-driven twin overhead camshafts operating 16 valves. Again, maintenance-free hydraulic tappets are used. Mounted in the throttle body is a single electronically controlled injector which sprays fuel into the inlet manifold on the filter side of the throttle disc. So, how does the K-Series engine fit together? And what are the features of the 16-valve engine? First, the cylinder block. Perhaps the most interesting features of the block are the wet liners. But why use wet liners?
Wet liners are the ideal for an engine construction. They give us the minimum bore distortion which is possible to achieve. A top-hung wet liner has no forces on it which are distorting it as the engine warms up or goes under thermal load. That gives us the most consistent bore geometry, which gives us good oil consumption and good blow-by, which minimizes the loading on the breather system. Low friction allows us to use relatively low load friction rings. Good news all round.
Now to begin our engine rebuild. Lubricate the lower ends of the liners with engine oil. Be careful not to get any oil where the coolant will be in contact. Push the liners into place and tap home if necessary. The crankshaft is cast iron, with 5 main bearings and 8 balance weights. What is different is the way it's located. Instead of separate bearing caps, there's a one-piece bearing ladder. The bearing ladder and cylinder block are line bored together, so you can't change one without the other. All crankshaft shell bearings are selective fit to give the close-running tolerances required. Number and letter codes on the crankshaft and bearing ladder are used to select the correct color-coded shell bearings. How to select the right combination is detailed in the booklet that accompanies this video program. Two thrust washers are fitted at the center main bearing to control crankshaft end float and take clutch thrust loads. These thrust washers are only available in standard size and no regrind of the crankshaft is possible. The bearing ladder is sealed to the block with a special liquid sealer from Loctite. A sealant kit is available from Unipart, which contains everything you need to remove the old sealant and apply a new bead. Again, the booklet gives details. 10 small screws are used to provide a good seal around the edges of the ladder and hold it in place when the long through bolts are removed. Tighten these in sequence, starting in the middle and working outwards. At this stage, the crank is tight if you try to rotate it. But why is this?
The mechanism behind that comes back to the use of aluminium in the crankcase. It's a very lightweight crankcase, and the way it's machined, basically we load the crankcase to simulate the loads which the bolts apply, and then machine it with that load in place. Therefore, when that load is released, the crankcase distorts slightly, and that can be detected because of the small clearance between the crank and the bearings themselves. So the idea is that when the loads are in place, the bearing is round.
So that's the bearing ladder and crankshaft in place. Now for the pistons and connecting rods. K16 pistons are flat-topped with 2 valve head relief grooves. These pistons use a 2-piece oil control ring which is fitted with the top mark facing upwards. The word front must face the timing belt end of the engine. The gudgeon pin is offset towards the thrust side of the engine, so it's most important to fit the pistons the right way round. The gudgeon pin floats in the piston, but is a press fit in the conrod. A special tool is needed to remove and replace the pin. The connecting rods can be fitted either way round. A number stamped on the big end cap denotes the big end bore size. This is used in conjunction with a letter code on the crankshaft to select the correct color-coded bearing shells. Make sure the piston ring gaps are positioned away from the thrust side and aren't in line with the gudgeon pin. Apply a bead of liquid sealant around each oil feed hole in the oil gallery. The oil gallery also acts as a nut plate for the through bolts. Screw 2 of the through bolts into the gallery to make sure it's properly located before tightening its fixings. The oil pickup strainer and sump can now be fitted. There are 2 types of cylinder head used across the K-series range. There's a high-performance twin-cam cylinder head on the K16, whilst 1.1 and 1.48 valve engines use a common head. The K16 cylinder head uses a 1-piece bearing ladder to locate the camshafts. This bearing ladder contains the upper halves of 12 camshaft bearings, 6 for each camshaft. Oil grooves cast into the bearing ladder feed the hydraulic tappets and camshaft journals. Maintenance-free hydraulic tappets are used on all K-series derivatives. If the tappets are removed for any reason, store them face upwards to prevent oil escaping, and of course they must be replaced in their original bores. When the engine is rebuilt, some tappet noise may be noticed. This is quite normal and will disappear when the tappets have recharged themselves with oil. This is done by running the engine for around 2000 RPM until the noise ceases. Right, before we go any further with the engine rebuild, let's take a brief look at cylinder head overhaul. The K-series cylinder head is fully serviceable. Valve seat replacement and resurfacing, valve guide replacement and head face resurfacing are all possible. However, there are a couple of checks to carry out before you consider any work on the head. The first is camshaft bearing clearance. Remove all the valves and springs using a standard valve spring compressor. A magnet can be used to withdraw the cotters from the cap. Place the camshafts in position and lay a piece of plastigauge along each journal. Now, fit the bearing ladder and tighten the bolts to the correct torque. Loosen and carefully remove the ladder, then measure the thickness of the flattened plastigauge using the special gauge card. Check the clearance against figures in the repair manual. If this is excessive, repeat the test with a new camshaft. Camshaft end float must also be checked. Do this using a dial gauge. Again, if excessive end float cannot be cured with a new camshaft, then a new cylinder head must be fitted. If you find it necessary to grind or cut the valve seats, you'll need to check the valve stem fitted height afterwards. If the valves protrude too far through the head, measure from the top of the valve stems to the valve spring seats. Compare the readings against those in the repair manual. The valve guides can be removed and replaced using a stepped drift. One special tool contains the drift, depth gauge and nylon collar. All guides, inlet and exhaust, are fitted to the same depth. Cool the guides in a freezer for about an hour before drifting them in. A special tool must be used to remove and replace the valve stem oil seals. A common seal is used for inlet and exhaust valves. When you're working on this cylinder head, cleanliness is imperative. If in doubt, wash it out. Lay the camshafts into the head with the drive pins in these positions. This allows the camshafts to lie relatively flat and is also close to their eventual timed position. Carefully apply a bead of liquid sealant to the camshaft carrier. It is most important to apply sealant exactly as detailed in the repair manual, or you could block the oilways. But what is the reason for using liquid sealants on this engine?
There are two joints in particular where there's little alternative. They have to be metal-to-metal joints. That's the crankshaft to main bearing ladder and the camshaft ladder to head joint on K16. Since they have to be metal-to-metal joints, we must use a zero thickness sealant. Liquid sealants are the obvious solution. It's very important when those joints are broken that the surfaces are cleaned and prepared properly and that the appropriate sealants are reapplied.
On the 8-valve cylinder head, a separate oil rail, sealed to the bearing caps with O-rings, supplies oil to the cam bearing journals and hydraulic tappets. Remember to fit it. The K-series engine uses a completely new type of head gasket. It's a stainless steel gasket with molded seals for coolant, oil and breather passages. The gasket is fitted with special limiters which give exactly the right amount of compression on the sealant paths. Make sure you fit it the right way round. Before you fit the head, loosely fit the crank pulley and turn the engine to 90 degrees before top dead center. This is known as the crankshaft safe position. It's called safe because, set like this, the pistons will not contact the valves. Lower the head carefully over its two locating dowels and place the head bolts in position. Don't drop them in or you'll damage the first threads in the oil rail. Torque the bolts in sequence to 20 Newton meters. Now mark the head adjacent to the line on each bolt flange. Tighten each bolt in sequence about half a turn. Finally, tighten the bolts until the lines on the bolt flanges align exactly with your marks on the cylinder head. If you go too far, then loosen the bolt at least a quarter of a turn before trying again. Carefully locate all four camshaft seals and drift them into place. The same tools are used for removal and replacement of both front and rear seals across the K-series engine range. Don't forget the O-ring seal on the water pump before refitting. Identical gears are used for inlet and exhaust camshaft drive. The gears have IN and EX markings to indicate the correct position over the drive pins. Tighten the center bolts to the correct torque. Turn the gears so the inlet and exhaust marks are pointing towards each other, then fit the locking tool. Fit the oil pump and drift in a new oil seal. Don't forget to lubricate the lip of the seal and the protector sleeve. Lubricate the crankshaft boss and carefully pass the rear main seal over it. Gradually tighten the flywheel bolts to draw the seal into place with this special tool. When the seal is fully home, leave the tool in place for a short while to allow the seal to settle. Special micro-encapsulated bolts hold the flywheel in place, and these must not be reused. A locking tool is used to restrain the flywheel while the bolts are tightened. A spring-loaded tensioner is used for timing belt adjustment. On K16 engines, the tension spring is fitted to the center hole. On K8 engines, the spring must be in the lower hole. Make sure the crankshaft is in its safe position. 2 dots on the crankshaft gear should straddle a center line cast into the oil pump. Turn the tensioner plate fully clockwise and nip the screw up. Fit the timing belt, starting with the longest run between the crankshaft and exhaust cam. It's important to have as little slack here as possible. Mark the belt with an arrow to ensure it's refitted the same way. Now loosen the tensioner screws and push the belt towards the cover. This sets the spring to its natural position. Loosely fit the crankshaft pulley and turn the engine clockwise through 2 revolutions. This operation is most important. Turning the engine enables the tensioner to remove all slack from the belt. Finish with the timing marks aligned. Now tighten the tensioner plate screws to the correct torque. Finally, with the flywheel locking tool in place, torque up the crank pulley bolt. This tool is used to hold the clutch plate central as the cover plate is fitted. All K-series engines have an R65 transmission, mounted end-on. 4-speed, 5-speed, and 5-speed close ratio versions are available depending on the model. When fitting the exhaust manifold gasket, make sure the gasket is fitted with its shiny face outwards. The exhaust manifold itself has equal length tracts for good power balance. A Siamese downpipe is continued into the exhaust front pipe. This increases the effective length of the tracts, which improves both performance and economy. This technology is carried over to the inlet manifold, where long tracts improve torque at low engine speeds. The inlet manifold has a PTC heater to aid cold drivability. So, that's the engine rebuilt and ready to be dropped in. Let's take a brief look at how this is done on the new Metro. The top steering ball joints and track rod ends are split, and the hub assemblies then swung aside as far as possible for extra clearance. The gear change linkages can be easily damaged, so position them as close to the gearbox as possible and keep an eye on them. Lower the engine into the bay, checking for obstructions as you go. The starter motor must not be fitted at this stage or it will foul the radiator. Position the drive shafts squarely into the differential. The extra clearance gained by swinging the hubs away makes it possible to feed the drive shafts in as the engine drops into place. Now secure the engine mounts. Don't forget the coolant and oil before you attempt to start the engine. A strict coolant fill procedure must be followed or large air pockets will be left in the system. There are 2 bleeds on the Metro and 1 bleed and remote fill on Rover 200 series. The K-series design achieves true lean burn combustion. But what's the difference between combustion in the K-series and conventional engines?
Well, the big difference is this, that the combustion is under control. Therefore, it burns lean, very much leaner than a conventional engine can go. The consequence of that is we need very much less fuel than you do in a conventional engine. You can get high performance out of it without the traditional way of just having to throw lots of fuel at it. You can get low emissions because all of the fuel we're actually using. And after all, you know, if you don't use the fuel, it comes back out of the engine as emissions. We're actually getting to use all of the fuel. So it's economical, it's low emissions, and it's high performance.
K8 engines are fueled by a new constant depression carburetor, the K-series Integral Float Carburetor, KIF for short. There are 3 basic tuning adjustments. Normal idle speed, through this plastic capped screw, idle mixture adjustment with a Torx number 10 screwdriver, and finally, fast idle speed. Pull the choke knob out to the first detent and adjust to the correct speed. Remember, you must follow the correct tuning sequence as shown in the repair manual. K16 engines have a slightly more sophisticated injection system, all controlled by a single ECU. Sensors placed around the engine keep the ECU informed of the engine's needs. To tune the K16 engine, microcheck or co-best must be connected into the system through the diagnostic socket alongside the ECU. These system testers lead the operator through a sequence using on-screen instructions to either tune the engine or diagnose faults. Before we round up, let's take another look at the most important points of the K-series engine. The K-series through bolts screw into an oil gallery to hold the cylinder head, block and bearing ladder in compression. The push-fit wet liners are sealed at the base by two O-rings, which must be replaced whenever the liner is removed. All crankshaft bearings are a selective fit. Codes on the crankshaft, bearing ladder and big end caps determine which of the color-coded shells should be fitted. No regrind of the crankshaft is possible. The bearing ladder and camshaft carrier are sealed using a special liquid sealant. Don't use anything other than the recommended sealer. With the through bolts removed, the crankshaft will tighten up. This is quite normal, but turn the engine as little as possible until the bolts are fitted. Never turn the engine with the timing belt removed, or the valves will contact the pistons. The timing belt has a 96,000 miles service life with no tension checks in between. However, if you remove the belt any time after 48,000 miles, then renew it. The booklet accompanying this video covers all these points in detail, along with a quiz to test your knowledge, and don't forget to return your answer sheets for marking. So, after all this, how do the team feel about the K-series engine?
I'm delighted with it. The reports that we've had so far from the field bear out the results that we achieved within our own development testing, and so far we're chuffed.
It's magic. It's tremendous. What's so nice about it, and what really does set it apart, is we set out to achieve something with a K-series engine. It's been a long, hard work. We set ourselves objectives, we struggled up to them, we slipped back a bit, we struggled past them, we set the next objective. We had a lot of work, really painstaking work. It wasn't, oh, we threw it together and we were lucky and it worked. We earned it every step of the way. And when we got there, we're almost surprised it actually does what we said it would do. And it's not just that, it's that our customers at every stage, whether it's service or manufacturing even, service, and our customers represented by the press, technical press, people out in the field, they're telling us it's good, they're telling us it works, it's right. And that's the real thing. It's fine from our biased point of view to tell us, to say, yeah, we like it's a great engine. That's easy to say. But when your customers who are paying money for it tell you it's a great engine, it's a great engine.